So I'll go ahead and I'll jump into another very important concept in artificial neural networks. We have seen the basic building blocks of artificial neural networks. We have seen what gives them complexity and nonlinearity, but there's another building block, programmatically speaking, that is very important as well. There are the tensors that help us to represent the complex data that builds up the inputs, the activation functions, the neurons, everything in a neural network. And one very typical characteristic of AI training data is that it's very complex, it's highly dimensional. And just to show an example here, in image classification tasks, for example, when we work with pictures to be classified by an AI model, or pictures to have objects detected or faces detected in their contents, we usually don't have just a table of samples by features, as you usually find in other numerical data sets. Usually you find three-dimensional data. For example, here in this image, we have an image width in pixels. We have an image height in pixels as well. So those are 2 dimensions. And then we have a color channel that has it adds another layer of complexity, another dimension, with the 3 colors and the color intensities. And all those color intensities are represented by numbers. So just in a simple image classification example here, we already have several numbers. We have all these numbers organized in a structure that has 3 different dimensions. And most of the data in AI, they're even more complex than that. If you imagine a video, for example, time is an additional dimension in this data. And you can keep going as you add more characteristics or sub-features into this large set of multidimensional features. So one way that all the AI frameworks found out, they developed to deal with this complexity in a more organized and structured way, was to create a new type of variable called tensors. So tensors, they're not just used by TensorFlow, actually. Tensors are used by PyTorch, TensorFlow, Keras, any AI framework. So that's like a standardized type of variable in AI. And they basically define nearly all the elements of your AI framework, your AI training, AI architecture, the neurons, everything. So your input data, the way it is when you import it into Python, it will not be supported. It will not be loaded by your neural network. You first have to convert that into a tensor. So then the tensor can leverage the power of the GPUs, of the GPU acceleration, and it can be used by your neural network for doing the training of large and complex data and large and complex neural network architectures. All that organized structure is to allow the GPU acceleration, allow easier implementation and easier training of your neural networks, and faster and more feasible training as well. So first, starting from the top, your input data must be converted into tensors, your network layers as well, all the hidden layers that I was talking about, all that organizational structure of layers of neural networks with a depth and width, everything in that structure, they're usually represented by tensors. Also, in a neural network, you have many weights, so many slopes, and you have many bias or intercepts, because you have hundreds or even thousands of neurons in your neural network. So you're gonna have hundreds or thousands or even more weights and biases. And it can get very messy if you don't organize that structure. So that's why the tensors are used to represent and organize the structure of weights and biases terms as well. And also the algorithm, the optimizer, the gradients, used in the backpropagation that optimizes the weights during the training process are represented as well by tensors. And when you generate, after you train your model and you generate the predicted values from your neural network, also the output, the predicted values are tensors. So if you want to save that output into an Excel spreadsheet, for example, those values are going to be in tensor format, and you're gonna have to convert them back into whatever numerical format that you want to use to export. So everything in AI is, everything in building, implementing neural networks is in tensor. Everything is represented in tensors. So that's why it's very important to understand that they exist and understand what they are, but it's not such a complicated thing. Usually in neural network programming, we will have access to very high level design frameworks. They will do all the heavy lifting for you. They will take your data and convert into tensors. You can do that with a simple one-line command. And internally, when you create a new layer, when you add an activation layer, when you train your model, all that will be automatically converted into tensors internally. You don't need to convert one by one of them into tensors. So most of the tensors that I was talking about, all those elements that are converted into tensors, they are done, this conversion is done automatically. The only thing that you really have to worry about when you are implementing neural networks is to make sure that your input shape, the input data structure, the number of samples by features, for example, and the neural network architecture, especially the input layer and the hidden layer sizes, they match to your input data shape. The most common problem in neural network programming is in those shape mismatches. So I just wanted to highlight that that's the key to understand this data structure. So then you can match your input data shape, the input shape of your input tensor data to the neural network architecture. So then you avoid to do that mistake that is very common in neural network programming, which is mismatching those two important things. Tensors are not just made to represent complex numbers, complex data sets. They are very flexible and they can generalize any numerical representation. Even a simple number, a scalar, like this example here, an integer, can be converted into a tensor. It can be represented as a tensor. For example, a vector as well, a small vector, a list, or a one-dimensional array can be represented by a tensor as well, can be converted into a tensor. Matrix as well can be converted to a tensor, and a three-dimensional array can be converted into a tensor as well. So if you're not familiar with this bracket syntax, I recommend that you learn a little bit more about that, because you're gonna see that often in multidimensional data in Python. So usually when you add a bracket here, you're just indicating that those numbers belong to the same rank or to the same dimension. And usually when you work with numerical data in Python or in any other programming language, you think of a three-dimensional image as having 3 dimensions, but in tensor language, they actually have rank 3. So instead of saying dimension, we say rank. So a scalar, for example, is rank 0 because it's just a simple number. It doesn't have any complexity. Then when we add one layer of complexity here, we group the numbers into one dimension. We call that rank 1. And then when we have, for example, a matrix where we have, let's say, samples by features, so 2 dimensions, or width by height, 2 dimensions, we call that rank 2, actually. And when we have a 3D array, like the 3-color channel image I was talking about, we're gonna have a rank 3. So the number of ranks is usually how we usually call the number of dimensions, but here we call that rank. So that's very important because dimension is going to have another meaning. And I will explain that in a moment. So all these conversions into tensors with different ranks are done to allow the GPU acceleration for doing operations with those numbers. So when you sum the results of the multiplication from the weights times the inputs, it's done through tensors, allowing GPU acceleration. When you multiply as well the weights by the inputs, it's also done through GPU acceleration. Computing the gradients as well, all those operations are only they are only allowed to use GPUs thanks to this tensor structure that communicates with the GPU the cores. So just to give a more visual representation, so that little vector is just one sequence of numbers enclosed into a list, for example. That would be a rank 1 tensor. Then if you want to represent visually what is a rank 2, you would have, for example, samples by features. You would have a table. It would be a rank 2 tensor. If you have a three-dimensional, that three-channel image, that picture that has width and height and then color channels, you would have a rank 3 tensor. If you have multiple representations of that rank 3 tensor enclosed into a sequence like that, for example, a video, when you have multiple pictures in a sequence where you have a fourth dimension of time, then you have a rank 4 tensor. And you can imagine adding multiple rank 4 tensors together, multiple replicates of a video, I don't know, or multiple channels of a video, multiple subfeatures. Then you're gonna have a rank 5 tensor, and you can keep that game on and on until you have a rank 6, rank 7, rank 8. So tensors are very flexible, and they allow you to represent any level of complexity in your data. And that is something that other types of variables don't allow you to do so efficiently, and they don't allow you to do using GPUs. So that's why tensors are so relevant in artificial neural networks. So usually when we talk about tensors, we talk about complexity in ranks, rank 1, rank 3, rank 6, for example. So usually you don't tell those complexity levels as, you don't call them dimensions, you call them ranks. And then the length of each rank is actually the dimension. I'll show a better illustration soon. So for example, a rank 2 tensor is a matrix. It is not a two-dimensional tensor. It's a rank 2 or tensor, or it has 2 ranks. That's how we use this terminology. And as I mentioned, the dimension of each rank is actually the length or the numbers, the count of numbers in each one of the ranks. So if we have a matrix that is 5 samples by 3 features, then we have dimension equal 5 at rank 1. This is the rank 1. And then we have a dimension equal 3 at rank 2. So this is the second dimension, rank 2. So this is usually how we describe a tensor. You never have to be so specific when you are creating your tensors. The conversion is done automatically. The programming framework will identify the rank for you. It will identify the dimensions for you, and it will do the conversion automatically. But this is important that you understand. In case you find any bugs in your code, you find any errors mentioning that the dimensions don't match or the ranks don't match, then you understand what the framework means by rank and what the framework means by dimension. So tensors are very important structures, and the neural networks work basically by transferring the information of these tensors from one computation to another, from one layer to another, from one neuron to another, from neurons to activations, from activations to outputs. So we can imagine the data flowing throughout all the way from the input layer to the output layer in tensor format. So that's how the data flows throughout a neural network. And all the computations related to neural networks are done on tensors. Yeah, and again, it's very important to understand the input shape of your input data tensor, because if the neural network receives a data that is not in expected shape, then you will report a wrong rank error, and then you'll be lost trying to figure out why your code failed. And when the data has the expected shape, it passes, it does all the calculations correctly. And there is another important concept to understand. Tuples are usually used to describe the complexity of the tensors. So that information that I was talking about before, this example of a 5x3 tensor of dimension 5 and rank 1, dimension 3 and rank 2, that information on their structure or their description is usually stored as tuples. So a tuple is usually a set of numbers enclosed between parentheses. So you can imagine that you're gonna have the information on the number of ranks of your tensor and the dimension of each rank in a list enclosed between parentheses, which is the tuple. So the most simple one that is has only one element is rank 1, would be a tuple like this. You just represent one rank with dimension equal 15, like this one here. So you have only one rank and 15 dimension. So this is like the vector example that I showed before, but that vector had only 2 values, I think. So imagine if that vector had 15 values. So its shape would be represented like that, its structure. If we had a rank 3, for example, we would have the rank 1 with dimension 2, rank 2 with dimension 7, and rank 3 with dimension 91 here. So this is just a description of what is the content and shape of that tensor. So saying that rank 1 has dimension 2 means that in the first dimension you have 2 values. Rank 2 has 7 values, and then rank 3 has 91 values. And you can keep going, increasing the complexity. You just increase the number of ranks here, the numbers here between parentheses. And here, for example, is just a rank 5, where all the ranks have dimension 3. So this is like a 5-dimensional array, 5-rank array with the same set of numbers for each one of the ranks. So it can keep going, it can keep getting more complex than that, but just keep in mind that the important thing here is to understand that when TensorFlow or PyTorch or any other neural network programming framework shows you diagnostics or an error, it will show you the shape of your tensor. For example, if there's a mismatch, it will show the shape of your tensor and the shape of your input, and the shape will be represented by a tuple like that. So the TensorFlow will report tuples as the tensor shapes for everything, for inputs, outputs, layers, and activations, and the shapes must match. You see me repeating this many times because it's very important, and it's the most common source of errors and troubles when programming neural networks.